Hello guys, what do I call you? Stats crew. Welcome back, Stats crew. Welcome to video 2 of week 10. In video 1, we talked about the basics of confidence intervals and constructed our first couple of confidence intervals. In today's video, I want to dig a little bit deeper into what these things are and some of the important concepts involved in confidence intervals. Also, I realized that I forgot to include a secret video question in video 1, so I'm going to put 2 of them in this video. The first secret video question answer is tomato juice. Tomato juice. The answer to the first secret video question for video 2 of week 10 is tomato juice. Okay, back to our regularly scheduled programming. So, important parts of confidence intervals. By the way, I'm going to say CI all the time, the letters CI, because confidence interval takes a long time to say and type. So whenever you see CI, I'm always talking about a confidence interval. I want to remind you guys, and this is so key, confidence intervals are our first tool in this class for statistical inference. We use them to make estimates about population parameters based on the sample statistics we've gotten. And I've given you some examples. Mu, think to yourself, which parameter is that? And you think, yes, that's the mean. We could say something smart about the mean based on x bar, the sample mean. What does our sample tell us about the population? In the recent videos, we've been talking about P, proportion. We've been saying something smart about the population proportion based on the sample proportion. We'll continue with proportion in this video. In the next video, we'll start talking about means. Okay. Here's one of those screens with a ton of information. Again, I always want to remind you guys, feel free to pause at any time. Also, these notes are posted on my website, so you can go there if it's easier to read. There's a lot of stuff on here. Take it at your own pace. I'm going to try to talk about all of it, but, look at it and decide for yourself if you feel like you understand. Last time, we found confidence intervals for proportion. Here is the formula that we talked about. We did this thing in example 1 and 2 in the video last time. If you don't remember this formula, you might want to go back to video 1 and practice those confidence intervals again, just to make sure you feel okay about them. One connection I really want to draw for you guys is that even though we're going to see lots of different confidence intervals, proportions aren't the only one. We could do means, we could do standard deviations, we could do 2 means, we could do 2 proportions. There's all sorts of different confidence intervals out there, but they all have exactly the same form. They all look like the one we've seen. And I wrote here a little bit more narration about the form you see for these things. Let's talk about these pieces. First, all of our confidence intervals are based off of a point estimate. And really, that's just another way of saying sample statistic. A point estimate is one single number that's our best guess for what we think is going on with the population. So usually that's going to be something like p hat, the sample proportion. That's what we saw up above. P hat is an example of a point estimate. X bar is another example of a point estimate, and there are others still. But that's always the beginning, and this thing, our best guess, that's always the middle of the confidence interval, right in the center. We take the result that we get from our sample, and that's our first guess. Of course, we have to go with the sample data, right? Tomato juice, sorry. Of course, we know that that estimate isn't going to be perfect every time, and that's why we need a margin of error. That's why we need the whole interval. There's got to be a range of values that the proportion could take. Next really important thing is the critical value. And that's that z-score that we've been finding in all of these problems. The critical value is how we express confidence in our confidence interval. It's a z-score, and specifically, it's the cutoff for the middle whatever percent. We've done middle 90%, middle 95%, middle 99%. I make up weird ones sometimes, like middle 98% or middle 80%. Whatever that middle range we're talking about, that's the confidence level. And whatever our confidence level is, that determines what the z-score is going to be. In this context, those z-scores are called critical values because they determine how wide the confidence interval is going to be. And these are always backwards problems. One thing I really want to emphasize, whenever you're looking for these z-scores, probably this is the easiest part to get confused about when you're first starting. These are always backwards problems, and they're always like middle percent problems, middle 90%, middle 95%. This thing is the cutoff for those middle values. There are a few that we use a bunch, and you might have accidentally memorized some of these things already, especially 95%. 90%, 95%, 99%. Those are all really common confidence levels that people use in the real world when they're doing this stuff, mostly just because they're nice round numbers. So you'll see those z-scores all the time. For example, 1.96, we've seen this thing like a dozen times in this class already. 1.645 is another common one, and 2.575 is also another common one. Your textbook, by the way, rounds this to 2.8. Whatever, it doesn't really matter. If you don't know how to find these, those are things you should be asking me about on my online office hours. I do lots of examples here, but if you're still feeling confused, that's okay. Just ask me for help so I can give you some more examples and we can figure out what's giving you trouble. And the last thing in the confidence interval equation is the standard error. The standard error is just the standard deviation of the sampling distribution. That's the spread of the sampling distribution. We've seen in our work that we always get a normal curve for the sampling distribution. And sometimes it's wider, sometimes it's narrower. That's the standard error. And we've already seen one example of this. For proportions, it's all the square root stuff. Square root of p, 1 minus p all over n. We'll see similar examples in the future. There's nothing on this screen right now that specifically helps you solve the math problems we're going to do. But if you want to understand the stuff that we're doing, I think this is all the really important, interesting stuff. This is what you're going to do every single time you find a confidence interval. Okay. Another really important quality or measurement in our confidence intervals is the margin of error. And if I could make a gesture to express margin of error, I'm doing it right now. Big margin of error, small margin of error. Means exactly what you think. How far off might our point estimate be? Whenever you take a sample and you get a sample proportion or a sample mean, of course, you know that's not going to be exactly right for the whole population every time. But how much wiggle room do you expect to see? How far off might it be? That's the margin of error. And it's pretty easy to find mathematically. Mathematically, the margin of error is just everything after the plus or minus. Let me just scroll. I'm about to scroll up to show you really quickly. Remember our formula here. This stuff, I'm highlighting it right now. That's the margin of error. Everything after the plus or minus. We'll see lots of different confidence intervals, but it's always the stuff after the plus or minus, so it's easy to find. And here, just to be super clear, for proportions, the margin of error is this stuff that I've got highlighted, z, the critical value, times square root p hat, 1 minus p hat all over n. Now, of course, we're always hoping that the margin of error is small. Makes sense, right? Of course, error seems bad, so we don't want much of it. We want this thing to be small. That's going to give us a precise estimate for what the true population parameter is. Zoop. We hope to zoom in and see exactly what's going on. The good news is we do have some control over this, and that's really what this lecture is going to be about. What factors influence the margin of error, and what sort of control do we have over them? I think it's a really interesting topic. In particular, there are two big factors that affect the margin of error. The first one is sample size. I think sample size does the thing that you'd expect it to do. Bigger sample size sounds good, right? Smaller margin of error sounds good, right? Well, it really does work that way, and that's kind of a good thing. If sample size goes up, if n goes up, then margin of error goes down. You can actually see that directly in the formula. I pasted it in here, and I'm just bringing your attention to it right now. Do you see what I highlighted there, the n? In the margin of error formula, you're dividing by n. N is on the bottom. So it makes sense that if n is bigger, that's got to make the margin of error smaller, right? If you divide by something big, the overall result that you get has to be something small, right? And that's good. That means if we increase our sample size, the thing that we hope for happens. We get a smaller margin of error. That's what we really have control over. The other big thing that affects margin of error is the confidence level. And I've got some bad news for you on this one. Of course, we hope to be more confident. But think about what that means. Confidence is tied to how much of the distribution we're encapsulating. Here's middle 50%. Here's middle 80%. Here's middle 90%. Here's middle 99%. If I want to get all the way to 99.999%, my hands just keep going out and out and out and out, right? If I'm going to be more confident that I got the true population value, I need to increase the width of the confidence interval to make sure that the true population parameter is in there. Now that's a bummer though, because that means if there's a bigger confidence level, our interval has to get wider too. Bigger confidence means bigger margin of error, and that is definitely a bummer. This is one where we kind of lose out, but it's the price we pay. If we want to make sure that we've captured the true population parameter inside of this confidence interval that we made, we got to make that thing wider. No other way about it. So whenever we're designing a study and deciding what our confidence level should be, there's a balancing act that has to go on. A really common question for students to ask me at this point in class is, okay, Professor Miller, why don't we just choose a 99.9999999% confidence interval? If we can pick how confident we want to be, why not just be super duper confident, right? Wouldn't that be good? Well, I guess it's kind of good in the sense that you'd be sure your confidence interval worked. But it's also kind of bad because that means your confidence interval would have to have a really, really, really wide margin of error. So even though you'd be sure that your true population value is somewhere in there, how would you know exactly what it was? Like, maybe for an example, we've talked about the gender ratio at Denison. What if you estimated that between 10% and 90% of Denison students are female or male or whatever? Between 10% and 90%. Well, almost certainly that's true. You can be very confident that the true proportion of Denison students who belong to either gender is between 10% and 90%. But that's also not very helpful. What exactly is it? We didn't get a very precise estimate for what's going on. That's the real problem we're running up against. But we can do a little bit of planning. Let me show you some examples. We can do some planning for margin of error. Here's another big block of text. Feel free to pause to take a look at what's going on here. Since sample size affects margin of error, maybe we could design our study or our survey or whatever that we're doing to have a big enough sample size to ensure that our margin of error isn't too big. So in other words, we're thinking about it like this. If I want to do a study that's, super, super accurate, however accurate that I want, I can plan in advance for how big the sample size has to be. Unfortunately, mathematically, this is a pretty easy question to answer. We're asking a question about the sample size, so let's figure it out. All we're doing in this technique, math-wise, is we're solving for n in the margin of error formula. We know what the margin of error is. I've got the formula for you right here. I know that the margin of error is blah, 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 blah. Well, what if there's a particular margin of error that I have in mind, and I want to figure out the sample size that would guarantee that? If you do a little bit of algebra, here's how the formula works. All I'm doing there, algebraically, is solving back for n to get n by itself in that equation. You don't have to memorize this. You can always have this written down on your piece of paper, on your note sheet when you're taking the quiz. But maybe you want to think about this for a second and make sure you agree with me that this makes sense. There's one little problem with this formula. We want to figure out n, but there's a p hat that shows up in there. In other words, a proportion. If we don't know what the proportion is, what do we put there? Well, there's two options. If you do have some prior estimate, use that. If you think you already know what it is, go ahead and use that estimate. But a lot of times, you might not necessarily have any idea. Maybe this is the first time you've studied this particular population. So if you have no idea, if you don't have a prior estimate, use p hat equals 0.5. To be super clear, just to type this in, that means then n is equal to 0.5 times 1 minus 0.5 times z over MLE squared. If you don't know, use 0.5. That might seem kind of random. It actually turns out that 0.5 is the worst case scenario. It gives you the biggest possible margin of error. And if you've ever taken calculus, this is an example of an optimization question. And if you really want to, I will totally talk you through this optimization problem in office hours. I think optimization is really cool, and calculus is awesome. I guess that's why I'm a math teacher. All right, let's do an example. This connects to a previous example that we thought about in video 1. We constructed a confidence interval for the proportion of Denison students who watch the Netflix show Love is Blind. And in that problem, we had a sample proportion of 26.7%. And we had a margin of error of 9.4%. Now, I didn't say it exactly like that last time. You might want to go back and take a look to make sure that that makes sense. We didn't explicitly compute the margin of error. This is a great practice problem to go back and look. Okay, 9.4%. It's kind of big, right? How about, let me even just show you. I've got my notes right here. Here it is. We are 90% confident that the true proportion of Denison students who watch Love is Blind is between 17.3% and 36.1%. Kind of a big range. So what if we wanted a better estimate? We'd need a bigger sample size. Last time, we had a sample size of 60 students. So if we want to do better than that, we're going to have more than 60 students in the sample. Let's take a look. For this example, I'm going to use the same confidence level, 90% confidence. That's what we did last time, so let's keep it the same just to make it easy. Let me come back. Suppose that we wish to conduct a new study where we hope to estimate the proportion of Denison students who watch the show Love is Blind with a margin of error no greater than 5%. Let me add in here, use the same 90% confidence, because we need a confidence level. In that case, how big does our sample have to be? Well, let's think about this. The formula that you saw a second ago is n equals p hat 1 minus p hat z over MOE squared. We're going to use that formula right now. And we know most of this stuff. Here we do have a prior estimate. 26.7%. By the way, that was 16 out of 60. That was the number from that sample survey. We did a study. We found 26 something percent. Let's use that. For Z, since 90% confident, Z is equal to 1.645. Again, that's because there's 90% in the middle. That means there's 5% in each of the two tails. You can find the Z-score from the Z table. Talk to me in my virtual office hours if this number doesn't make sense. And the margin of error that's desired here is 5%. We want to be accurate to within 5%. Okay, cool. That means we've got all the information we need. Let's find what n has to be. Before we find what n has to be, I think it's time for the answer to secret video question number 2. I don't know. Vegetable peeler. The answer to secret video question number 2 is vegetable peeler. Shh, shh, shh. I was eating carrots. I like carrots. Vegetable peeler is the answer to secret video question number 2 for week 10, video 2. That's right, we got 2 of them. The first one was tomato juice, and the second one is vegetable peeler. All right, let's find out. All right, using our formula, I've got p hat equals 0.267 times 1 minus 0.267 times quantity. My z-score is 1.645, and the margin of error that we're hoping to get is 0.05. That's 5%. All that stuff squared. And And when we ask our calculator, it looks like it's 211 something. Of course, I can't have 0.83 students. That would be messy. That's a really funny joke, by the way. We can't have 0.83 students. That would be messy. You guys should all have laughed at that joke in class when I told it in person. It's too late. We need n equals 212. The next biggest thing, we're trying to make our margin of error smaller, so we need n to be bigger. And that's that. In order to obtain a margin of error no greater than 5%, we need to sample 212 students. The end. So whether or not that's reasonable for us, now we've got a target. If we were designing our study, we'd be able to say something smart about how big that sample would have to be in order to get a margin of error of 5%. If we wanted a smaller margin of error, we'd need more students, and we could do that math too. Cool. That's it. That's the whole technique. Let's do one more example. Here's example 2. On example 2, it says, suppose we wish to estimate the proportion of Denison students who are vegetarian. And let's suppose we don't have any previous information available to us. We haven't done any studies. We have no idea. We want our estimate to be accurate to within 1%. And I need to tell you guys too, with confidence level of 95%. Let's say we're doing a 95% confidence interval. How many students must we sample? Before we get too far into this question, maybe let me just rephrase this. We hope to construct a 95% confidence interval with MOE no greater than 1%. That's the deal. We want to make a confidence interval. Our confidence level is going to be 95%. I just made that up. And we want it to be pretty accurate. We want a small margin of error, no more than 1%. How many students? What's n? Okay. The work itself is going to be really similar to what we did before. There's only one little tweak here. Since we don't have a prior estimate, we're going to use p hat equals 0.5. The worst case scenario. Since we don't have any idea what the proportion of vegetarians is, let's use 0.5. That's going to give us the biggest possible margin of error. So we know for sure we're not going to mess up. All right, then let's think about what we've got. Our formula, p hat, 1 minus p hat, let me clarify, this is for n, times z over MOE squared. This is the same formula from up above. We're using p hat equals 0.5 because there's no prior. We're using z equals 1.96 because confidence is 95%, just like we've seen on previous examples. Ask me about this in office hours if that doesn't make sense. And for our margin of error here, we're going to do 0.01 because that's 1%. Cool, that's it. Let's plug it in. 0.5 times 1 minus 0.5 times 1. Oh, I'm sorry, I said 1.95. I meant 1.96. My bad. 1.96 over 0.01 squared. Now, this is kind of bad news. Uh-oh. I picked this example on purpose, but it seems like maybe we got a little bit greedy when we were designing our study. If we were hoping to have a margin of error less than 1%, we would need a sample size of 9,604 Denison students. Well, crap. There aren't that many Denison students. We would have to do a full census if we wanted to make sure that our margin of error was that small. So that's not useless. The moral of the story here, we're too greedy. We can't have such a small MOE. Try again. Now, on like the quiz on Noble or something like that, of course you can tell me 9,604 and that's the correct answer. But practically speaking, if we were investigators and we wanted to find out about Denison students, we might just have to accept the fact that it's not possible to have such a small margin of error. If we're going to take a sample, any reasonable sample of Denison students, we'll have to accept that there is some margin of error, and it's going to be at least more than 1%. Maybe we need to adjust our expectations and allow for a little bit bigger margin of error. Alright guys, that's the end of this video. Hope you enjoyed. I think margin of error is a really cool topic because this is just such a practical thing. You know, you guys might not realize it, but you're exposed to confidence intervals all the time. Whenever you hear a statistic in the news or some other source, people don't tell you what the margin of error is, but there is still always a margin of error attached to every number that you hear. Maybe now that we've done a little bit of the math behind margins of error, you can be a more savvy consumer of those statistics. When people quote you off, oh, 26% of people say this, you might think to yourself, well, what's the margin of error? I mean, if the margin of error is only like 2%, oh, okay, well, I bet that's pretty good. But if the margin of error is like 15%, then you might think to yourself, hey man, you're full of shit. Or maybe you could say it more politely. All right, guys, I'll see you in the next video. I'll post some practice problems too. Next time.